Hello and welcome to the 7th video in the GLOOM series, where we're building a first-person shooter style game completely in TypeScript. So last time we started setting up our level system and we got basic camera movement in place so that we could move around and debug. And this time we want to go ahead and start filling out our level and get geometry to generate so that we can actually visualize our levels and start having this feel more like a game. One of the first things that we're going to need to do is we're going to need to add an asset. So if you recall, in our map file, we actually are referencing a texture that we have not yet added to the project. So under assets, we're going to need to create a new folder, call this textures, and then we want to right click and reveal that in Explorer. And I'm going to paste in a tilemap texture that I have created ahead of time. It doesn't contain too many tiles yet, but it's big enough to be able to handle a lot of the tiles that we're going to want to use. So the texture, you can't see it here because it's transparent, but this is a PNG and it goes all the way down to here. And these are some of the basic tiles that I've created in the meantime to sort of give us enough that we can start to build a level with, and we'll fill these out more as the game dev continues. But for now, this will be more than enough tiles to use in our actual process. So you can grab this from the GitHub repo. By the time this video is published, that will be available. Cool. So now that we have our tile map in place, we need to actually put something in place to load that. And we also need to obviously load this level file and be able to read all that in. So the first thing that we need to do is we need to load in our JSON file. But before we can do that, we need to first create a couple of classes to actually hold this information. So under source, I'm going to create a new folder. I'm going to call that level, and I'm going to actually move level TS and automatically update the imports. And then under that, I'm going to create a new file, and we're going to call this level data.ts. And this is actually going to hold the data that we're going to load for our level from this file. So it's going to give us a nice class that we can use. We're able to take the contents of this file and feed it into that class. So obviously we'll want to start by exporting a level data class, and to it we're going to want to add a bunch of public properties that we're going to be filling in. So we need the width and the length, the sectors, which we're missing a sector class, we'll create that in a moment, the tile map path, which is that string here, the tile width and tile height, which is the tile width and each tile width and height, so in our case 64. Then our two-dimensional array of texture IDs for the floor, the wall, and then the ceiling, as well as our initial spawn position. So before we continue any further, let's create a sector class. So create a new file under level, we'll call it sector, and we're going to export a sector class. And this of course includes a reference to an enumeration. So let's go ahead and create a new file for that. And we're simply going to export an enumeration containing our sector types as we mentioned before. So we have none, open, and wall. Obviously in sector we'll need to add an import for that. So our sector holds a few pieces of information. It holds the type, it holds the light color, it holds the grid position X and Y. So it's actually it's pretty straightforward, but it's a nice data structure. Instead of trying to hold all these things individually and sets of array, it gives us a nice data structure to be able to access this information in. So we're actually done with sector. There's not a whole lot to that. Back in level data, we'll need to add our import to sector. And then we'll actually want to add a public constructor, which takes in our raw JSON content that has been loaded. And we'll populate this data with that raw JSON data. So I'm just going to paste some more code here and add our missing imports. So the way that this is going to work is we're going to check for the existence of each one of these fields before it exists. And anything that is required and missing, we're going to throw an exception. So the first thing we're going to look for is the spawn position and then the X and Y positions components rather of that spawn position, because we need all that information to tell the player where to start. And then of course we'll create a spawn position, which is a new vector 2, convert the x and y to number, and then we'll have our spawn position. So the other fields are going to be handled very similar to this, so I'm actually not going to go through them piece by piece. I'm just going to paste some code here. And you can see that we go through width, length, the tile map, the tile width, tile height, and then our two-dimensional arrays for our wall texture IDs, floor and ceiling texture IDs. Next, we're going to loop through our map and get our sector information. And we're going to do this Y first and then X. And the reason that we'll want to do that is because if you're reading a file, you're always going to want to go row and then column. And we need to maintain that same order for everything that we do. So within this loop, we'll need to create a new array for the Y row in our sector's 2D array. And then at that point, we can loop through the X for each one of those individual sectors. This is where we actually parse out the information. So we'll actually push a new sector, and we're extracting the sector type from YX, the light color from YX, and then of course we're passing X and Y to the appropriate parameters in the sector constructor. That's really all there is as far as reading the file for right now. Eventually when we add entities, we'll need to add a little bit more information to that, but we'll tackle entities much further down the line. Just for the record, entities are items like pickups and enemies and things like that. So it's going to be a bit before we actually add that stuff, so I don't want to add that in here yet. Okay, so back in level, we're going to need to add a constructor because now we need to pass something to it. As you may have guessed, we're going to be passing level data to our constructor. So this level data will already be loaded and parsed by the time we get to the level, so that the level class doesn't have to worry about any of that parsing information. It can just take the data as is and stand things up. So underneath scene, we're going to add a couple of private variables. We're going to add a isLoaded flag to let the engine know whether or not this level has been loaded, or if it's currently loaded, currently loading rather. So in the constructor, we're just going to keep a copy of the data, and I'm actually going to move the internal scene creation to the constructor as well. Next thing we'll want to do is we'll want to add a couple more accessors. So we'll add one for isLoaded and one for spawn position, of course making sure to update the imports as needed. Next we're going to be changing up our load method a bit. So all this stuff is actually going to be going away here very shortly. So the first thing that we need to do is add a loader, a texture loader rather, so that we can actually load the tile map texture. So obviously be sure to add the import there. And then we're going to tell the loader to go ahead and load the tile map texture. And we're going to pass it the tile map path, of course. And then we're going to tell it, once that has loaded, we're going to call onTextureLoaded, and we're going to bind it to this. And we're actually not going to pass an error or onload status for right now, callbacks. We probably should add this eventually, but for now I just want to get things up and running, so I'm going to skip that step and just leave it to do there. So obviously the next thing that we're going to have to add is the onTextureLoaded. So onTextureLoaded will be private and take in a texture, so we'll need to add that import. And what this is going to do is it's going to wait to actually load the map until the texture has been downloaded. And this is so that we can be sure that we properly have the texture in memory so that we can use some of its properties in order to generate the data that we need to generate. So before we can start loading anything, we need to create several more private properties. So we need to keep a copy of the tile map texture. We also need to calculate how many tiles wide and how many tiles high the texture accounts for. And then we also need to keep a copy of the map material that is generated. And we'll get more into that in a bit. And of course we'll want to get rid of the 3 prefix if it happens to be in there, and make sure that any existing imports are there. We'll also want to add sector light colors, which is a 2D array of light colors. And this is just for a quick lookup that we'll need later. I'm not going to touch that for now. but we'll definitely need that in the future. So on texture loaded is sort of the meat and potatoes of where most of our loading code happens. And so what we're going to need to do is first obviously store off a copy of the texture. This particular game, we're actually going to want to take that texture and we're going to want to use the nearest neighbor filter for the min and mag filter. And what that'll do is that'll give us that sort of pixelated look that we are going for that was present in a lot of retro games. Next, we're going to want to extract the actual width and height of the texture itself. So we do that by taking the texture object, getting its image property, and then pulling width. And the image in the TypeScript definition is just listed as any, but it actually is an HTML image element. So we can be reasonably sure that that is going to include the width and the height properties. Next, we'll calculate the tiles wide by taking the texture width and dividing it by the tile width. And we'll do the same for tiles high and tiles height. And for the sake of debugging, we will go ahead and print this information to the console so that we can have a quick look at the data that's being loaded in to be sure that it's correct. Next, we'll want to set up a material for this. So we'll need to add vertex colors. And the way that this material is going to work is we are going to provide vertex color information to handle the lighting later on. And we're going to pass the tilemap texture as the texture map to be used in this material. And we only want to create one of this material to be used for the entire level. So we're creating one map material and we'll be using that throughout the entire thing. We're also going to take this physics world and we're going to move it down here. So for now, we're just going to set up the physics at that level, and we'll add the rest of the physics information later as we continue. Really quickly, also in load, just to prevent any confusion, I'm going to remove this test code because we don't need it anymore. The only thing that load is going to do is it's actually going to trigger our texture to load, and then once the texture loads, we'll then load the rest of the level. So the way that this is going to work is we're going to have an array of plane geometry objects. And we're going to create one plane geometry for each wall, one plane geometry for each floor, and one for each ceiling. Those will all be loaded together with this material into a single mesh, which will then become the level. And this is to ensure that we're not making a ton of draw calls to a ton of objects throughout the scene. Our entire level's geometry is made just using one draw call. So it's extremely efficient in that regard. So next we're going to set up our sectors. And similar to how we read in the data, we're going to be looping through this in the Y direction first, followed by the X direction. I'll go ahead and fill in the sector light colors for now as well, even though actually while I'm at this, we might as well just implement the light colors instead of moving that to a future video. So yeah, we're actually just going to do that now, and I've rethought it, and it doesn't really make sense to push that out to a video of its own. So we will create a new row in our two-dimensional light sectors array, and then we will loop through the width or the x-axis of our data. We're going to just save off the current sector data into a local variable so it's easy to access. We'll go ahead and create a new 3-color object using the sector's light color, and we'll assign it to our two-dimensional array. And again, this is a 2D lookup that we'll use later. We're not going to use it right now, but trust me when I say later on we're going to be thankful that we have this. Okay, so the next thing we're going to do is we're going to switch on the sector.type. The first case that we're going to implement is going to be the open sector type because it's quite honestly it's the easiest to implement. But before we can do this, there's a few utility methods that we need to create. And before we can create those, there's a couple of utilities and a class that we need to actually create as well. So under core, we're going to create a new file. We're going to call this rectangle2D, and we're going to export the class named rectangle2D. I'm not going to really explain this because it should be pretty obvious as to what's going on here, We have an XY and a width and height. And then in our utilities class, we'll actually need to add a couple of new functions to this as well. So we're going to have a new static assign vertex color method, and it's going to take in some geometry. It's going to take in a light color, a face count which defaults to 2. I'll get more into that in just a second. And then verts per face which defaults to 3. So in our case, we're going to be using this with planes. So any geometry in the world is always going to be made up of triangles. And so since we have a plane which is a square, that's made up of 2 triangles. Each triangle is a face, hence face count of 2. We also have 3 vertices per face. So a triangle has 3 points, hence the 3. Pretty straightforward stuff. And so what we're going to do is we're actually going to assign a color to the vertex information for each one of these verts according to the geometry passed in and the light color passed in. And this will give us our sort of our lighting effect that we're looking for. So the first thing we're going to do is we're going to loop through each face. Within each face, we're going to loop through each vertex. So for each one, we're going to update the geometry face at index I, and then its vertex color at index j, and we're going to set it to a new color of light color. And actually as an optimization, yeah, we don't need the new call there. We can just set it to light color. Okay, so after all that's done, we also need to tell the geometry that the elements need a update. So this will actually trigger something within threejs to actually say, okay, we've applied these updates, upload that data to the new vertex data to the shader. Since those updates only actually happen whenever we change something, we need to set this flag to true anytime we assign the vertex color. And that's all there is to adding the lighting info. Okay, so the next method is a little bit more complicated. So we need to set the plane texture coordinates from a source rectangle. And so what that means is if we look at our texture, we only want to use a portion of this texture at a time. And so what we'll need to do is tell the texture coordinates that we only want to use, say this square or this square. And in order to do that, you have to make some calculations on the UVs in order to actually tell OpenGL that that's what we want to do. And so that's what this method is actually going to calculate. So the source rectangle represents the size and location of the individual tile that we want to use. And then the texture width and texture height is used to get a percentage of that, because UVs are indexed from, they're in a range from 0 to 1 as far as the texture is concerned. So we'll need the width and height of the actual texture to calculate that. And then we'll take in the texture coordinates that we'll be modifying. And then we also have some booleans here whether or not we want to flip the X or Y axis, because there may be certain scenarios where we want to do those things when we're making these calculations. So within this, the first thing we're going to want to do is we're going to want to get the min and max for the X and the Y axis. So what this is going to do is it's going to allow us to create very straightforward lines of code without having to include all of this information. It's just basically shortcuts, if you will. Next, we're going to actually be modifying our texture coordinates. So this is going to take the first texture coordinate out of our 2D array, and it's going to set its X and Y. And whether or not we have the flip X on determines whether it uses max or min. And then we take that min or max and we divide it by the texture width to give us our X position. And then to get our Y position, we actually take our, again, if we're flipping Y or not, we take our min or max and divide that by the texture height. We subtract that number from 1.0 to get our final result, because textures are actually loaded upside down when you load them in code. We're going to need to do that a total of 6 times, so 1 for each of our texture coordinates. So if you recall, in assign vertex color, we wound up with 6 vertices. So this is making an assumption that we only have 6 texture coordinates, which is fine because all of the geometry that's going to be using this will have that. So in this case, that's an okay assumption to make. If we need to expand this further, it would likely be much more advanced, and it's not something that I necessarily want to do right now. So we take 0, 0, 0, 1, 0, 2, and then 1, 0, 1, 1, and 1, 2. and we make all those calculations, and we apply those changes to the texture coordinates. And that's it, really. So it's just a nice convenience method that we can call from someplace and not have to do all this logic in line every single time we want to execute this. So back in the level, now that we have our utility methods defined, we actually need to make a private method to construct a plane for us using those new methods. Under private onTextureLoaded, we're actually going to create a new method, and this method is called buildPlane. So let me just add some imports here. So it takes in a vector3 position. That'll be the center position of the plane. It takes a source rect that'll be used and calculated out from what tile ID we want to use. It takes a texture width, texture height, light color, and then rotational degrees on the X, Y, and Z axis. And the reason for that is we want to use the same function whether we're creating a wall, a ceiling, or a floor, so we can rotate those things independently. And then it's going to return a plane geometry. So the first thing that we're going to want to do is create a new plane geometry as we did before. Next, we're going to assign the vertex light colors, making sure to add the import. After that, we're going to set the plane's texture coordinates from the source rectangle that is passed in. Next, we'll perform the required rotations based on what was passed in. So we'll check to see if this exists for each one of these, and if it exists, we'll perform a rotation. If it's undefined, we won't. Make sure to add the import there. Finally, we'll translate the wall geometry to the appropriate position, and then we'll return it. Back in our onTextureLoaded, for our sector type open, we're going to calculate the texture coordinates first for the floor mesh. And so the first thing that we do is we get the texture ID. From there, we calculate the row and column based off of that. So the column is gotten from a modulus of tile ID, and then how many tiles wide we are. And then the row is simply tile ID divided by how many tiles wide we are. So in other words, it goes top to bottom, left to right. Next, we calculate out our source rect. So we take column times tile width for the X position. We take row times tile height for the Y position. And then we simply pass in the width and height for the width and height of the source rect. Next, we build out the floor by calling this build plane, and we pass it a new vector3. So we pass X for X, we pass negative 0.5 for the Y axis, which puts it down a little bit below the camera. And then we pass Y and the Z of the vector3. Remember, when we're translating from 2D to 3D, that's how we make that translation. We pass our source rect, our texture width and height, our light color casted to a color. So the constructor for the 3 color takes the string. So we can just create that on the fly. And then we have a X rotation of negative 90 degrees. That just takes the plane from facing the camera and rotates it 90 degrees backwards so that it faces upwards instead. And then there's no X and there's no Y and Z rotation. And then we push that into our geometries array. So the same exact process is actually followed for the ceiling. And the ceiling is just simply using the texture ID for the ceiling instead. And then the only difference between this and the floor is it's raised up by 0.5 instead of negative 0.5. And its X rotation is 90 instead of negative 90. Other than that, it's pretty much identical. So above this, we want to add a new case for sector type.wall. In this case, we're actually going to be building up to 4 geometries for this, plane geometries. So one thing I forgot to do around open is I want to surround this in curly braces to keep this scoped. And we'll need to do the same thing around wall. But anyways, so we need to calculate the texture coordinates, of course, using the wall texture ID. And then from there, we'll need to build basically each side of the wall if needed. However, before we do this, there's a couple of convenience methods that I want to add just to make things a little bit easier. We'll want to add a method called getSectorSouth, which takes in a sector, add the import for that, And what it does is it takes in the sector and returns the sector that is to the south of the passed in sector. So in this case, it's sector.y plus 1. And we want to make sure, of course, that's within the bounds of our array. And if it is, then we will return that individual sector. Otherwise, we return undefined. And we'll want to do this for all the directions. So we'll want to add 3 more of these in here. One for north, that of course goes negative along the y-axis. One for east, that's positive along the x. And one for west, that is negative along the x, and returns in the same fashion. And that way we don't have to do this xy calculation in the middle of our code. We can simply just ask for it further up when we actually need it. For our walls, we're going to start with the south-facing wall first. And we're going to take the current sector and get the south wall. So we want to check that sector, and if it exists and the type is open, we want to create this geometry. So in other words, if this direction is adjacent to an open cell, we want to create wall geometry. Otherwise, we do not. So if the cell is empty or another wall, we're not going to be creating geometry that will never be seen anyways. These same steps are followed for north, east, and west. However, I should point out that there are some differences in what is passed to this build plane. So obviously, the XYZ is going to be different in each direction. So for south, we're always going to be taking in the X. The Y is going to be always 0 so that it's centered at on the 0. And then Y is going to have 0.5 added to it in order to offset that to the north, which is technically south facing. We take in source rect, text width, height as normal, same with light color. And in this case, we don't need to perform any rotations whatsoever because the south facing is actually the default. This is the same as our test plane that we initially created, so we don't actually have to change anything. North is almost the same as south, except it's negative along the y-axis, and we have a 180-degree rotation on both the x and the z axes. Other than that, it's identical. Same for east facing and west facing. The only difference here is that we take the y and pass it to z as is. On the y-axis, we still passing 0, and then for east, we add half a unit, and for west, we subtract half a unit. All the other information is exactly the same. The only difference being is that on east, we rotate on the y-axis 90 degrees, and on the west, we rotate by 270 degrees. So these degrees and rotation have all been tested so that the textures are also facing the right way. So we want to make sure that the textures aren't like rotated to the side or upside down or something like that. So all these rotations take all of that into account to create a geometry that looks proper. And then what we're going to do is for wall, we're eventually going to want to set up physics, but that is going to be done in a different video. So I'm going to put a to-do there, and then that is pretty much done for now. We don't actually need to do anything here for empty sector types, so we don't need to fill in a case for that, so I'm just going to skip that for now. Okay, so the next thing that we're going to need to do is combine all these geometries into one. So we're going to create a new geometry object, making sure to import that, obviously. And we're going to want to iterate all of the geometries that we've added to our geometries array at the top here. And we're going to say combined.merge and then G. And then once the geometry's been merged, we can actually dispose of it. So we don't want to leak any memory here. So we want to make sure that that these objects are disposed of correctly once we've actually, we don't need them anymore. Just to further that concept, we want to set geometry's length to 0 because we no longer need those geometry objects anymore. So now that we have everything in one giant geometry, now we can actually create our sector group mesh. which there are going to be additional optimizations that we're going to place on this later. But for now, we're going to have everything just render as one giant mesh. So this giant mesh is going to take our combined geometry, and then it's going to use our map material that we created earlier. And we're simply going to add that to the scene. And then any additional processing of level information will be done at this point. Once we're done, we're going to set this is loaded to true. And we're also going to fire off a message to say that the level is loaded and pass the level along with it. So this could be used to notify the engine that a level is loaded, or maybe the UI system, anything really that needs to know that a level has been loaded. Okay, I believe that actually finishes off the level for right now. So in order to actually kick all this off, there is one more step that we have to add to the engine. So in order to actually make use of all this, let me just get rid of this renderer right here. In order to actually make use of all this, we need to add something to the game. So in the game, under Start New, we're going to modify this because obviously we don't have the data that we need anymore to actually be able to handle this. So we're going to temporarily hard code a map, but eventually we should allow maybe for some debug options to be able to load a new level file. And before we actually fill that out, I'm going to go towards the bottom here and create a couple private methods that we're going to need to hook in order to make all this happen. So the first one is a private load level file where we pass a file path string. And to do this, we're going to create a new XML HTTP request. And to that, we're going to attach an event listener, which listens for the load event, which will call this on file loaded, and then pass the XHR object when that actually happens. And we'll fill that out in a moment. And I'm not going to handle errors right now. Eventually, that's something that probably should be done, but for now, I'm just going to put to do in there. And we're going to go ahead and open the request and then send the request to the server. And so obviously that means that we need our on file loaded to be filled out. And so we're going to create a new private on file loaded that takes the XML HTTP request object. And what we want to do here is we want to check the status of that to make sure that it's greater than or equal to 200 and less than 300, because anything outside of those ranges indicates an error. So before we actually load a new level, we want to unload an active level if it exists. So we need to add an import here. And then what we'll do is we'll unload the current level and then set it to undefined. Now we have not created an unload, so let's add that. So it'll be a public unload, return type void. And for now, all we're going to do is set this is loaded to false. We're going to fill that in a little bit more later, but for now, that will be should be sufficient. That should be public, not private. So once we've done that, we'll want to load up the new level. First thing we'll want to do is we'll take the response text, which is a string, and we'll parse it as JSON and save that off to an object. And then next, we'll create our level data object. Obviously, we'll need to add an import for that. And we'll pass it the JSON object as it expects. Next, we'll instantiate the level, passing it the level data, and then we'll call load on the level. Now, the concept of level loading is not something that existed prior to this video, so we're actually going to need to add a couple more things in to handle this properly. So in Start New, of course, we'll need to actually load the level. I'm going to put a big fat to-do in here that says that this should be menu-driven. This is not something that we should just be loading. We should probably pass what level we're loading in here. But for now, this will work just fine. And another thing that I'm going to check that's just sort of debug code is I'm going to check the query string for a level parameter. And if there is a level parameter, I'm going to get its value and store it in level override. And that's going to allow us to basically change the query string in the URL to load a specific level that we want to test. And so we're going to check to see if that exists, and if it does, we're simply going to create a new string containing the assets maps path and the level name, and then append JSON to that. And then we'll call this.load level file. If it does not exist, then we're going to auto load the first level for right now. And this should be triggered in the UI, so I'm putting this in here again as a reminder to myself that this really needs to be handled properly. So that will actually load the level and get things running for us. Next, we actually need to handle some of this properly, because we don't want to be doing any of this logic whatsoever here if we do not have a loaded level. So we're going to wrap all of this in a utility exists call. And not only do we need to check to see if it exists, but we also need to say if this level is loaded, then we can do all these things. If it doesn't exist and or it's not loaded, we should not be doing any of this. So this is sort of a safeguard as well as a pseudo optimization to make sure that we're not trying to execute these things at the wrong point in time. Okay, I believe that is everything we should need to do. So let's build this and run it. And we got nothing. Internal scene of undefined. Okay, so that is the renderer not receiving the active level. Okay, I know what this is. So in the engine, we're always passing active level and the active camera to be rendered, even if it's not loaded yet. So we actually need to perform the same exists check. So utilities.exists game.active level, and then we also need to say we need to check that the active level is loaded before we actually render. And that should fix it. So we'll build, run, and we still have nothing. Oh, we're getting a 404. It's trying to load a file that doesn't exist. So this A0M0, I had A0M1. So let's build that, run. There we go. So as you can see, we have our scene loaded up, and we can sort of maneuver around it a little bit, and we can see that the only geometry that was rendered or created rather was on the inside. So none of these cells or sectors rather have geometry except for the inside of them, or the part that's facing the actual open sector next to it. And you can see that our lighting is working as well. So yeah, I think this is probably a good place to go ahead and stop, because I'm sure that this video has gone on long enough. So thank you guys so much for watching, and please like and subscribe, and I will see you guys next time.